Morning. Okay. So here we have a wave. And if you go from peak to peak, that's a wavelength. That's one wavelength. Or you can also go from trough to trough. You guys know what a trough is? Okay, trough to trough is also a wavelength. And I'm not going to write wavelength there. I'm going to write the symbol for wavelength. And I want you to look at the wave itself and watch how I draw this symbol. Does that kind of look like half of the wave, right? So you draw like that, and then you draw a line down like that. And that is the Greek letter lambda. And it stands for wavelength. So wavelength is pretty easy to visualize because you either go from the peak to peak or the trough to trough. So if we compare the wavelength of our second wave, what can you say about the wavelength of this second wave compared to the first wave? The wavelength is shorter, okay? Now, we're going to talk about frequency. Frequency is the number of times a peak or a trough, but I'm just going to say peak to make it simple, the number of times a peak passes a point per second. The number of times a peak passes a point per second. Now, to illustrate what that means, if I have, this is my wave, waves travel like this, okay? They go, and if this is my point and it's moving, it goes 1 peak, 2 peak, 3 peak. Yes? That's probably about 1 every second or so. So that would be like 1 wavelength per second goes past that point. Yes? Now, if we then decrease our wavelength, but it's moving at the same speed, 1 peak, 2 peak, 3, 4, 5, 6, it's about 2 per second, yes? Okay, so if we double the frequency, if we half the wavelength, we double the frequency. So as wavelength gets shorter, frequency gets higher. Does that make sense? Okay. So if you have a long wavelength, your frequency is going to be low. And we're going to write our symbols in here as well. Wavelength, of course, you start at the top and you bring it down and then kind of like a swoosh. And then you draw it down and to the left, just a diagonal line. That is our wavelength. And what unit do you think we measure wavelength in? The base unit. We can do fancy units later, but what's our base unit for wavelength? Meters. Meters. Okay, so it's in meters. Frequency, I am so sorry, physics has a sensible sort of symbol for frequency. It says F for frequency. I'm like, yes, that makes so much sense. Chemistry chooses the other symbol for frequency, which is the Greek letter nu, which looks like a V that's like traveling quickly, right? So it kind of gets, it's like a curvy V. Okay? And that is the Greek nu. All right, and frequency is the number of times per second. So it's really just a number per second. Yes? And so the unit is just per second. Okay, so our unit of frequency is 1 over seconds. Or we can write that as, does anyone know how to write that in a different way? S to the negative 1, yep. And there's actually another unit as well, and that is Hz, which stands for hertz. So it's 1 over second or second to negative 1 or hertz. You can see any one of those, and they all mean the same thing. Energy is nice and easy. The symbol for energy is E. Okay, and what's the unit for energy? Joules. Joules. Okay, so there we have a long wavelength means a low frequency. It also means a low energy. And if you think about this, a wave that kind of goes like this, it just kind of seems lower energy, doesn't it? Compared with a wave that goes like this. That seems higher energy. Like in order to do it, it just takes more of my energy. Okay? So if we have a long wavelength, we have a low frequency, and we have low energy. If we have a shorter wavelength, our frequency and our energy are high. Now, do you need to remember all of these symbols, or are they provided for you somewhere in case you should forget? Where do you think you might find them? On your booklet. So let's go take a look on our data pages, page 6. Okay, and you can see here that we have a couple of formulas. This section is very much physics-ish. Yes, this little section, not all of it, but this little bit, because you see, oh, look, we have formulas, and we just chuck some numbers into formulas. These two formulas are related to one another. You might have to use one of them. You might have to use both of them. You might have to combine them into one formula, and I'll show you how to do that later. But if you're like, I don't remember what any of these things stand for, where can you look? Over on the side. See, it says E is energy, nu lambda is wavelength. And by the time, if you go and take a science degree, you too will be able to go to Greece and read the street signs. I finished a science degree and then I went on a backpacking trip in Europe and I could read the street signs. It was pretty cool. Okay, and then there's a couple other things that show up. We have an H, okay, and that is just Planck's constant. And you'll notice, how many sig figs do we have in Planck's constant? 4 sig figs. C stands for the speed of light, because when we're talking about waves, we're talking about electromagnetic radiation. And a lot of electromagnetic radiation is light. We have visible light, which has various wavelengths. We have UV light, which has a higher frequency. We have infrared, which has a longer wavelength and a lower frequency. And we'll also, in chemistry, be dealing a little bit with X-rays as well, okay, which are also higher frequency. There are other forms of electromagnetic radiation as well, but we're not really concerned with microwaves because they're too long range for atoms. And we're not concerned with, what are the other ones that are too long? Radio waves, also too long, okay? And we'll go through the whole electromagnetic spectrum later, but for now, we're mainly gonna focus on visual light because we're all so familiar with it, yes? So the speed of light, these waves, these are photons. They're particles of light and they move through space, okay? So this is light waves. So they travel at the speed of light because they are light. And again, there's 4 sig figs here. And they also give you Avogadro's number, which I'm going to draw your attention to because how many sig figs do they give you in Avogadro's number? They give you 4 sig figs. Now, I don't give you 4 sig figs because I would have to rewrite all the mole unit and the solutions unit and the stoich unit and change all my answer keys from chemistry 11, which uses 6.02 times 10 to the 23 to chem 11 enriched, which technically we should be using 6.022 times 10 to the 23. Okay, so I trust though that rather than me having to go and do all that work, you guys are okay with just remembering when you go to the AP exam, use the 4 sig fig version. Chances are you probably won't even have to use that number. It doesn't come up that frequently. Might come up in like the electrochem unit or something like that. But anyway, 4 sig figs, 4 sig figs, 4 sig figs. Okay. So back here, this just reiterates that light is measured by its wavelength in nanometers, nm, and its frequency in hertz or seconds to the -1. Okay, so that's just what we said before. And a wavelength is between 2 successive crests or peaks or 2 successive troughs. And you guys should now be able to do those little exercises on the right. So I would like you to complete them right now. And when you're done, just give me a little wave. Get it? A wave? No? Okay. Just do the exercises. Okay, so if we have a long wavelength, the frequency will be low. If it's very energetic, what kind of wavelength? short. If we have a high frequency, the energy is high. If we have a short wavelength, the energy is high. And if we have low energy, the frequency will be low. Or sorry, low. And if we have low frequency, the wavelength will be long. Okay, awesome. And this is just reiterating that the wavelength, the symbol is lambda, and we measure it in nanometers. And since we are focusing on visible light, that is, the range is from about 400 to 700 nanometers. Okay, and you should just become familiar with that. 4 to 7. So think, I go home. When do I get home? I get home around 4, and then maybe I do some homework till around 7, and then I have dinner. I don't know. That sounds like a bit long, but you know, you can just make something so that you can remember it. Okay, so 400 to 700. Now, you should also be able to quickly convert that into meters, because if we go to use one of our formulas, like say this one, right, and say we combine it with this other one where we have energy, I'm going to be working, energy is in joules, yes? And a joule is equal to, does anyone know what it's equal to in its base units? A joule? It's a kilogram, meter squared per second squared. Okay? And what that means is that if I am working with joules, I cannot be working in nanometers. I must be working in regular meters. Yes? So I need to be able to quickly convert from nanometers to meters, and it helps if you remember that nano means 10 to the negative 9. And if you forget that, guess what's on your data pages? Nano, 10 to the negative 9. Yes? So you can just take the nano and replace it with (10 to the negative 9). Do you remember doing that in the summer? A little bit? Okay. So yeah, that's the quick way to do it. And chances are you will just be doing a calculation with this, so you don't even have to change it into scientific notation if you don't want to. You can just leave it like that and chuck 400e negative 9 into your calculator. Yeah? But while we're here, let's see, can you write 400 times 10 to the negative 9 in scientific notation? And can you write it in standard notation? Give it a try. Oh, and let's put a decimal at the end of these numbers so that we have some sig figs in there. Okay. So to get into scientific notation, you need to have how many numbers in front of the decimal? Just 1 in front of the decimal. Okay, so 1 digit in front of the decimal. I should say 1 non-zero digit, but I think at this point probably that goes without saying. Fingers crossed. And because I have moved my decimal place 1, 2 positions, that means that this number got smaller by 10 to the what power? I moved my decimal place 2 places. So it got smaller by 10 to the 2, or you could say 10 to the negative 2, whatever. It's just by a factor of 100, okay? That means that our power of 10 has to get bigger by 10 to the 2. If one side is getting smaller by 10 to the 2, the other has to be getting bigger by 10 to the 2. So 10 to the negative 9 would become 10 to the negative 7. Okay? So that's in scientific notation. Standard notation, how many places would you have to move your decimal? Nine places to the left. So you go 3, 6, 9, and so you'd have 0, 0, 0, 0, 0, 0, 4, 0, 0. 0.000000400 meters. Just because you might come across them again, what is the symbol for millimeter? We all know it is mm. Micro, what's the symbol for micro? It's a funny looking M. It's the Greek letter mu. And the nanometer is, of course, nm. I don't think we need to write these numbers in standard notation. I think you're probably okay with that. I also use this for enriched stuff for my grade 9, so that's why some of this stuff is here. But let's think about it. A millimeter, now remember milli is 10 to the negative 3. Micro is 10 to the negative 6. And micro is 10 to the negative 6. And nano is 10 to the negative 9. So, how many times bigger is a millimeter than a micrometer? How many times bigger is a millimeter than a micrometer? 10 to the 3, which is how many? 1,000. A micrometer, which is 10 to the negative 6, is how many times bigger than a nanometer? 1,000. And a millimeter, 10 to the negative 3, whoops, is how many times bigger than a nanometer?
100,000.
You're so close. 1 million. And one thing that you'll notice about most of those metric prefixes is that they're all powers of some flavor of 3, some multiple of 3. Yeah? We've got 10 to the positive 3 is kilo. We've got 10 to the negative 3 is milli. There's a few exceptions, centi and deci, but most of them, if we look here, we have a 9, a 6, a 3, a negative 3, a negative 6, a negative 9, a negative 12. They're all 1/1000th of each other, or they're 1,000 times each other. And that's because I think that when we're writing numbers, you know, if we leave a space in a number, we leave it at the thousands position. Or if we write a comma, we leave it at the thousands position. Or we'll do a comma at the millions position, right? So that's kind of how we organize our numbers. And I think that's why we use powers of 3 sort of as our main chunks. Yeah? So the chunks of the metric things mostly are by thousands. All right. You are going to practice, and I know this seems silly, you're going to practice drawing lambda a few times. So you're going to go shoo, shoo, shoo. You can make the sound effects with me if you want, or not. Choo, 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 choo. So you go down first, and then you also go down the other way. I don't know what they teach in elementary school anymore in terms of writing, but like so many people write so weird now. Like I'm just like, oh my God. Right? And it's like so inefficient for people too. It's like doing your O that way. Oh God, it's not like I don't know. Oh. And then anyway, just things work better. Yeah, if you do cursive, it is helpful.
But now they don't.
I know. And I don't have like a big hang up about cursive, but I feel like it's just useful in terms of learning how to form your numbers and letters. Like I feel like penmanship has gotten worse over the years. Anyway, not all of you. Some of you have beautiful writing, but anyway. Now you're going to practice writing new a few times. I can't really draw, so I have to make sound effects along with my drawing. Hertz, seconds to the -1. There we go. There's a few little exercises down here. So you're going to... Actually, no, we don't need to do that. We've already done that. Seconds to the -1. You've drawn your little frequency. That's fine. Now, it's up to you whether you want to color your wavelengths. They are labeled red, orange, yellow. So if you don't feel a need to color, you don't have to. I do have lots of pencil crayons here of all various colors. So you can feel free to help yourself. And if you want to do it some other time, that's also fine. But what I want you to notice is that you can see who has the longest wavelength and who has the shortest wavelength. Who has the longest wavelength? Red is the longest wavelength. And who has the shortest wavelength? Violet. Okay. And in case you never learned this in elementary school, there was someone in block 2 who had not learned it. I'm always shocked at what doesn't get taught. How do you remember the order of colors?
You just do.
Okay, and it's fine to just do, but if you ever have trouble, if you're like, I cannot remember the order of the rainbow, and you're like, I'm thinking of it, I can't think of it, Roy, G, Biv. Roy, G, Biv. Red, orange, yellow, green, blue, indigo, violet. Okay? I'm always shocked at what doesn't get taught in elementary school sometimes. Because like in grade 12, when we've got some indicators that like have color combinations, and I'm like, what color do red and blue make? And people are like, I don't know. Or I'm like, what colors come together to make orange? I don't know. It's okay. I'll teach you next year if you've forgotten or if you never learned in the first place. In the meantime, maybe over the summer, go home and play with some paints. See what you get. Okay? But for now, I would like you to do these little exercises here. And once again, give me a little wave when you're done. Okay?
Oh, you need this one?
I saw Sally doing that.
Okay, now that you've like not finished coloring, what color of visible light is the most energetic? Which is most energetic?
Violet.
Violet. Which color of light has the longest wavelength? Red. Which has the highest frequency? Violet. Is green light more or less energetic than orange? More. Does yellow light have a longer or shorter wavelength than blue light? Longer. And indigo, does it have a higher or lower frequency than green? Higher. Okay, excellent. All right. Do you remember the wavelengths of visible light? How many nanometers? 400 to 700. 4 o'clock to 7 o'clock. So then red light would most likely have a wavelength of 700 because it has the longest wavelength. And violet light would be around 400. Okay, and now you get to do a little thought puzzle for number 14. I'm going to let you think about that. Okay, think about which is more stable. Is it 1 or is it 2?
Which transition would involve three?
Wait, never mind. No.
3 to 2. 3 to 2.
No.
Because
To the potential.
dense. This is more further out than this. That's why it would require more energy to go to 2. You get it? So this has to go to this, or this has to go to this. But which one involves greater change in potential?
So 1 or 2, which is more stable? The charges apart or the charges together? Together is more stable. Okay. 2. Least stable, obviously, then would have to be 1. So as we go from position 1, which is high potential energy, to position 2, which is low potential energy, are we going to release energy or are we going to require an input of energy? We're going to release energy, yes? And is that going to be endothermic or exothermic? Exothermic. Now, when I say exothermic, in these particular cases, we're probably not going to be giving off heat. We're going to be giving off light, okay? But it's the same principle, okay? Which transition either from 1 to 2 or from 3 to 2, which would involve the larger change in potential energy? 3 to 2. Oh, that's crazy. Okay. So which transition, 1 to 2 or 3 to 2, would be more likely to give off red light? One to 2 because it's a smaller change in energy. And violet light would then be 3 to 2 because it has a larger change in potential energy. Okay, and that is it for that. And what I'm going to get you to do is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. You're going to form groups with 2 girls and 2 boys in each group. Okay? 2 girls and 2 boys in each group. Go find yourself some people. Are you guys not in forming groups? Okay, please stop doing that. And you're going to join a group. You need to go find a group that needs boys. 2 girls, 2 guys in each group. And we have one group that just needs 1 guy over there. Yes? They don't fight. Either the boys or the girls. Nobody bites. Nobody bites. I swear to God. And Jade's fun. Jade, you're so they need to. Oh, you have to. Perfect. And Jonah? There you go. You're with Edward. Excellent. Now you're going to need your book and you're going to be working on the puzzle, which is on the next page, page 5. You'll want a calculator as well.
I do.
Before you start the Poggle, make sure you give each other your names if you don't already know them. Maybe tell them what grade you're in and tell them something that makes you happy. It could be your pet, it could be ice cream, it could be sleeping, whatever it is that makes you happy, just tell people. Okay, so your name, your grade, and something that makes you happy. You're on page 5.